And there's been a lot of debate in the literature about how green biofuels really are. So the corn-based ethanol experiment that we ran as the part of the Energy Security Act in 2007 didn't go very well. People figured out pretty quickly that wasn't a really sustainable way or environmentally friendly way of addressing climate change, right? It led to land use change and increased food pricing and lots of water quality issues from the fertilizer used to grow the corn. So how are we going to make biofuels in a way that is more sustainable? We've done some research to look at what is present in algae. So what do you do with the protein fraction? What have people published on? Starch fractions, there's pigments in there. So what are all the different parts that we would want to go after? And then what have people already patented or published on as a use for that fraction? We've thought a lot about what order you pull stuff out in. So from a systems engineering perspective and an optimization perspective, do you get protein out first? Do you pull lipid out first? Do you digest what's left and try to recover some energy out of it? Do you apply it for fertilizer? So a lot of research around the systems of what order you build out these processes in. And depending on what your incoming algae feedstock looks like, you might change the process to optimize for that. The other tool we used here was life cycle analysis. So why aren't algae biodiesel plants standing up all over the country if it makes sense that this is the second or third generation feedstock to make biofuel? These are the life cycle stages for algae. So you have to grow it, harvest it, get lipid out to make biodiesel from. You have to convert that lipid into biodiesel doing a transesterification reaction, and then you got to dispose of all this stuff at end of life. So this red path is what the proposed, according to DOE, path forward is. And these numbers in red are the megajoules of energy at each one of these stages. And this is to make 10,000 megajoules of energy as biodiesel out. So we already lost just on the cultivation stage, right? We've already put more energy into the system than we're ever going to pull out as biodiesel alone. And we went through and said, what's all the stuff that's out there that people are talking about? And either photobioreactors, doing harvesting in a different way, doing this transesterification step in a different way, and then what kind of credits can we recover from the other 70 to 80% of the biomass that's not going to biodiesel? So we're trying to work on this greener path and looking at the chemistry and the engineering around improving this transesterification step, and then what other fractions we can recover at end of life. So our goal here was to develop an improved extraction and conversion process for biomass to fuels. And we're going to use carbon dioxide to do that. So CO2 is a pretty cool thing. So it's regulated as a pollutant by EPA. But if you take carbon dioxide and you put it under really high temperature and pressure, it behaves as what's called a supercritical fluid. So in this, I just took some pictures of our reactor. So this is hexane on the bottom, and this is carbon dioxide. And if we increase temperature and pressure from this window to this window to this one, at the end you can see they're fully miscible. So CO2 starts to behave like hexane, like an organic solvent under temperature and pressure. So when you want to stop using it like an organic solvent, I just release the temperature and pressure, and I can recover CO2 as a gas and recycle it. And I'm left with whatever product I tried to solubilize. Okay, the other part for the chemistry I'm going to go through that you need to know is transesterification reaction. So this is the lipid or the fat triglyceride that you pull out of algae or corn or anything else that you're going to make biodiesel out of. With methanol and a catalyst, it's a three-step reaction. So you get 1 mole of FAME or biodiesel out, and you make the diglyceride. So I pulled off this bottom fatty acid chain. You do a second step, you pull off 2 chains. So you have a monoglyceride left and 2 moles of biodiesel, and then the last thing you wind up with is glycerol, which is soap, and you have 3 moles of biodiesel as a result of the reaction. So I'm going to come back to why this matters in a minute, but it's important to know we don't go just from triglyceride to biodiesel, but we go through 3 steps to get there. Okay, so the first first thing we want to know is, can we actually use CO2 to do this? Does it work? Is it efficacious? So I'm just showing you pressure, 3 different temperatures, and the amount of FAME we were able to produce out of the system, the amount of biodiesel, and it's normalized to how much we could produce using an organic solvent. So anywhere you see us reach 100%, our CO2 system is as good as an organic solvent system. So at some certain pressure and temperature combinations, we get there in terms of getting as much biodiesel out of the system just using CO2 as people do using organic solvents. Okay, and then it's not just how much you're getting out, but what it is. So those triglycerides come, these are different carbon chain lengths. So 12 carbons, 14 carbons, 16 carbons, and then how many degrees of unsaturation, how many double bonds are on that chain length. All you really need to know from this figure is here's the organic solvent system, and what it pulls out of our algae. And here's some different temperatures at 6,000 psi pressure and what we're able to pull out. So not only are we getting the same amount out, but it looks really similar in terms of the quality of what we're getting out of the system. Okay, is it better than what's out there, right? So now we know we can compete, but are we any better? Are we creating anything that's more sustainable or environmentally friendly? So this black gooey thing at the end is when you do an organic solvent extraction on algae, here's all the stuff that you get out. So you get out those triglycerides, those lipids you need to make biodiesel, but you pull out a bunch of other stuff at the same time. If we do this in CO2, we can actually control how much of this comes out as just triglyceride, how much of the other pigments and the other things we're pulling out. So I can actually get a cleaner product using CO2 than that organic solvent. We also wind up pulling out less nitrogen when I use CO2 than when I do an organic solvent extraction. The nice thing about that is if I have less nitrogen in my fuel, when I burn it in an engine, I release less NOx, less air pollution. So here's another benefit to using CO2. And then I think this is the most important benefit, and this is the one that when we go talk to algae companies, this is what they're excited about. We can actually use wet biomass to do the extraction to pull CO2 out, use CO2 to pull the triglycerides out. So I don't have to dry my algae anymore, which is a necessary step with the organic solvent. So we're beating the organic solvent system on performance, on cleaner product, and also on being able to use a wet starting material. So our other big goal here was, can we do this in one step? Can I put wet biomass in a system, flow CO2 in, get biodiesel out, and recycle that CO2? Right? This is beautiful, simple elegance if we can get this to work. I had a PhD student who spent a lot of time looking at different loadings of methanol, different temperatures, different pressures. So this should look like a design of experiments, right? So every combination we could. And there's one system condition that worked. So green is us being able to produce biodiesel out of the system. So we're around somewhere between 85 and 90% of what went in came out as biodiesel from the one reactor. So again, I'm just showing you some pictures of what this looks like inside our system. So we can make it all one phase, or we could start to manipulate whether we have a methanol layer and a CO2 layer, and you can see some triglyceride down at the bottom. So we're able to control the system conditions to pull out what we're specifically interested in. And the system doesn't just work for algae oil, you can use it for canola oil or palm oil also, and again manipulate conditions and the catalyst to increase how much of it gets converted to that green or the biodiesel that we're interested in. So here's where we are now in our system. So we can't do it in one step, we're not that slick. It turns out that if we want to extract other things besides the lipid, we need some co-solvents in there. So we have 2 reactors set up in series now. We do the extraction in the first one. When we pull out triglyceride, or what can be converted to biodiesel, we flow it into a reactor and we carry out the reaction. And then the other thing that we figured out is how we can recover different components out of this algae. So we can get things to make surfactants, we can get nutraceuticals out, and then whatever biomass is left is starch or protein, which both have uses that are out there. So this is not as quite simply elegant as what we wanted, but it's where we are in terms of the system that, like I said, just is patented and is now the basis of the company we're starting. All right, my last case study I'm going to talk to you about is materials. So we're working a lot on designing safer molecules and nanomaterials. So what is it about a molecule or a nanomaterial that makes it toxic? They're not all toxic. They're not all toxic to the same extent. So we're really interested in how do you make a nanomaterial that serves the function you need it to, but does not bring along the toxicity. This again is a really urgent need. If you look at the market penetration of nanomaterials that are happening and what's proposed, they're coming onto the market. There's been a lot of research around the risks for nanomaterial, whether it's worker exposure or consumers being exposed or what's happening in end of life. And what really drives this work is if I have a bottle or a cup of a clear liquid and it's on a table and I say to you it's super toxic, that's really dangerous, what are you going to do? Leave it alone, run away, get out of the room, right? Because I didn't give you any information about why it's toxic or how it's toxic, right? I didn't tell you how to drink it or that you had to put your hand in it or it had to volatilize. I just said it's really toxic. And there's a lot of research going on now, nationally and internationally, about why things are toxic, what makes them toxic. And if we understand the mechanism of toxicity, we, again, as engineers and designers, can design so that that mechanism can't be exploited. So, I mean, nanotech, I'm sure you guys are all really familiar, right? So it's anything that's less than 100 nanometers gets defined as nano. Lots of really interesting applications that people are looking at for nanoparticles on the application side, and we're interested on the implications of these materials. So we're specifically looking at carbon nanotubes, so they're like graphene oxide sheets rolled around on themselves. They're a single layer, and depending on how you fold them, you get different structural permutations. So what controls the toxicity of nanoparticles? There's papers that say it's about shape, it's about concentration, it's about what's on the outside surface, it's about what the surface charge might be, it's how they agglomerate and form aggregates. Lots of debate about what makes these guys toxic. We did a study that said, okay, we want to look at some of these things, but they're all interrelated. So we're going to do a really systematic study. We're going to start with a single wall carbon nanotube, and then we're going to derivatize it. So we're going to put different functional groups. These are just 9 different functional groups on the surface, one at a time. So we looked at this one first and put it on the outside and saw what toxicity was, and then around to these 9 different functional groups. It turns out some of them, so here's my starting material in blue. These ones that are in red are all the functional groups that are more toxic than the starting material. But then here are these green ones that wound up being less toxic than the starting material. And this picture I keep showing you is bacteria that are dyed. So the ones that are dead are dyed red, and the ones that are alive or viable are green. So there are some poor graduate student who actually sits and counts red and green dots on these Petri dishes so that we know these figures about what's alive and what's dead. I will say it paid off, so she just got her first faculty job. It's tough research to do. It turns out you can start to look at some of these properties about what makes them